Now, let's move on our discussion to electrochemistry. Electrochemistry is based on the concepts of oxidation and reduction. Oxidation is the complete, net removal of one or more electrons from a substance, also called de-electronation, and an increase in the oxidation number of it. For example, when 2 electrons are removed from a copper atom, it is oxidized to form a cupric ion. Reduction is the complete transfer of one or more electrons to a substance, also called electronation, and a decrease in the oxidation number of it. More generally, reduction is the reverse process of oxidation. For example, when 1 electron is transferred to a silver ion, it is reduced to form a silver atom. When a piece of copper is immersed in an aqueous solution of silver nitrate, electrons transfer spontaneously from the copper atoms to the silver ions. That is, copper is oxidized by silver ion, while silver ion is reduced by copper. Such paired oxidation-reduction reaction is called a redox reaction. An electrochemical reaction is a process in which electrons are transferred between an electron conductor and an electrolyte. The electron conductor in contact with the electrolyte is called an electrode. Since electrolytes are not electron conductors, an electrochemical reaction must be an oxidation or reduction reaction, which takes place at the interface between the electrode and the electrolyte. The reactants and products can be either on the electrode or in the electrolyte. For example, in the electrochemical oxidation of lead in sulfuric acid, lead is the electrode. Both the reactant and the product, lead sulfate, are on the electrode. Pay attention, only lead is oxidized. Sulfate ion does not change its oxidation numbers. In the electrochemical reduction of ferrocyanide ion on platinum, platinum is the electrode. Both the reactant and the product, ferrocyanide ion, are in the electrolyte. Pay attention, platinum does not change in the reaction. It can be regarded as the catalyst of the reaction, known as electrocatalyst in electrochemistry. In the oxidation of zinc in zinc sulfate aqueous solution, zinc is the electrode. The reactant is on the electrode, but the product, zinc ion, is in the electrolyte. A complete circuit needs at least 2 electrodes. The electrolyte and electrodes form a device called electrochemical cell. The electrode at which oxidation takes place is called an anode. The electrons removed from the reductant leave the electrochemical cell through the anode. Pay attention that the direction of current is defined to be the opposite of the direction of the motion of the electrons. So, the current enters the device through the anode. It is another way to define anode. The current of the anode is called anodic current. The electrode at which reduction takes place is called a cathode. The electrons enter the electrochemical cell through the cathode to be transferred to the oxidant. So, the current leaves the device through the cathode. It is another way to define cathode. The current of the cathode is called cathodic current. For example, a voltage is applied to an electrolyte of ferric ions and ferrous ions. The oxidation of ferrous ions to ferric ions on the anode produces an anodic current. On the other hand, the reduction of ferric ions to ferrous ions on the cathode produces a cathodic current. The electrolytes in contact with the 2 electrodes may be different. In this case, there must be a junction between them, preventing bulk mixing of the electrolytes, but allowing certain ions to travel through it to maintain electrical neutrality within each electrolyte. A junction is usually a salt bridge, which can be a piece of filter paper soaked with electrolytes. Each side of the junction is a half cell. The electrochemical reaction in each half cell is a half reaction. To denote an electrochemical cell, a cell notation is used. It is composed of the formula of each electrode and individual substance involved in the redox reaction across the cell, with all other common ions and inert substances being ignored. The substances in contact with each other are separated by a vertical bar. It is common practice to represent the anode to the left and the cathode to the right, and to put electrolyte in the middle. If there are 2 electrolytes, they are separated by 2 bars representing a junction. Here, we use the Daniell cell as an example. In a Daniell cell, the anode is metallic zinc, immersed in zinc sulfate aqueous solution. The cathode is metallic copper, immersed in copper sulfate aqueous solution. The electrolytes are connected by a salt bridge. The electrodes are connected to a load, such as a light bulb. The anode half reaction is the oxidization of zinc to form zinc ion. The cathode half reaction is the reduction of copper ion to form copper. The overall reaction is the combination of the half reactions, that is, the oxidation of zinc by copper ion to form zinc ion and copper. In the circuit, electrons leave the anode, travel through the load, and then enter the cathode. Meanwhile, zinc ions from the anode half cell pass through the salt bridge to the cathode half cell. Sulfate ions from the cathode half cell pass through the salt bridge to the anode half cell, to maintain electrical neutrality within each half cell. There are basically two types of electrochemical cells, depending on the spontaneities of their overall reactions. In a galvanic cell, an electric current is generated from its spontaneous redox reaction. For example, when the two electrodes of the Daniell cell are connected to a light bulb, it becomes a galvanic cell. The overall reaction is spontaneous. Chemical energy in the galvanic cell is converted to electrical energy. An electrolytic cell drives a non-spontaneous redox reaction through the application of electrical energy. For example, when high enough voltage is applied to an aqueous solution of sodium hydroxide, water is decomposed into hydrogen and oxygen. This process is called electrolysis. It is well known that the decomposition of water is non-spontaneous. Electrical energy is converted to chemical energy during electrolysis. Now, let's consider the thermodynamics of electrochemical reactions. Consider a half reaction, in which a substance, O, is reduced to another substance, R. Z is the number of electrons transferred in the reaction. The reaction Gibbs free energy is given by the following equation. Here, phi is the electrochemical potential of the electrons in the electrode. It includes the contribution from Fermi energy and electrostatic energy of the electrode. F is Faraday constant. It is the absolute value of electric charge of 1 mole electrons. Therefore, minus ZF phi is the molar energy of electrons in the electrode. Electrochemical potential is related to potential energy. Thus, to describe the absolute value of electrochemical potential, the reference point must be specified. The electrode used as the reference is called a reference electrode. The modern standard reference electrode is standard hydrogen electrode. It is based on the redox half cell between hydrogen gas and aqueous proton, where both activities of hydrogen gas and the proton are unity. A schematic draw of a standard hydrogen electrode is shown here. The electrode is made of platinum. Hydrogen gas of 1 bar is bubbled to the platinum electrode. The electrolyte is a strong acid, whose pH is equal to 0. A hydroseal is used to prevent oxygen interference. The electrolyte of standard hydrogen electrode is connected to the electrochemical cell via the junction. Standard hydrogen electrode is not convenient in use. Thus, other reference electrodes are introduced, such as saturated calomel electrode and silver chloride electrode. The electrochemical potential difference between an electrode and a reference electrode, when both are in equilibrium, is called its electrode potential. By convention, the reference electrode is the standard hydrogen electrode. The standard electrode potential is the electrode potential when all the substances involved in the redox reaction are in their standard states. Since the half cell is in equilibrium, the Gibbs free energy of the half reaction is 0. Meanwhile, since the substances are in their standard states, their chemical potentials can be replaced by their standard Gibbs free energies of formation. As a result, the standard electrode potential is directly related to the standard Gibbs free energy of reaction, excluding the energy of electrons. For example, find the standard Gibbs free energy of formation of copper ion. The standard electrode potential of the redox reaction between copper ion and copper can be measured by the following electrochemical cell, where the electrode in question is connected to a standard hydrogen electrode, and the voltage between the electrodes are measured. The activity of copper ion is made to be unity, so that it is in its standard state. In this condition, the voltage between the electrodes is the standard electrode potential. It is about 0.34 volt. The standard Gibbs free energy of formation of metallic copper is 0. Thus, the standard Gibbs free energy of formation of copper ion can be calculated. The electrode potentials are related to the redox strengths of substances. A stronger oxidant is less stable. That is, its Gibbs free energy of formation is greater. That raises the electrode potential, On the other hand, a stronger reductant is less stable as well. That also raises its Gibbs free energy of formation but lowers the electrode potential. Therefore, higher electrode potential leads to stronger oxidizing ability of the oxidized form, while lower electrode potential leads to stronger reducing ability of the reduced form. The relationship between redox abilities and electrode potentials can also be understood using an electrochemical cell. When the oxidized form has stronger oxidizing ability, it takes away more electrons from the electrode, pushing up the electrode potential. When the reduced form has stronger reducing ability, it imposes more electrons to the electrode, bringing down the electrode potential. Here, I show you the standard electrode potentials of a few half reactions in aqueous solutions. Some features can be found from this table. First, the standard electrode potential of the proton-hydrogen gas redox pair is 0, in accordance with the definition of standard hydrogen electrode. Second, the standard electrode potential reflects the substance's redox abilities. For example, alkali metals are stronger reductants than hydrogen, since they have negative standard electrode potentials. Halogens are stronger oxidants than proton, since they have positive electrode potentials. These tendencies are accordant with the tendencies of electronegativity and ionization energy of atoms. Higher electronegativity means higher electronation ability, stronger oxidizing ability, and higher electrode potential. On the other hand, lower ionization energy means higher de-electronation ability, stronger reducing ability, and lower electrode potential. When a half reaction is in equilibrium but the oxidant and reductant are not at their standard states, the Gibbs free energy of reaction should be corrected using the activities of them. Replace the standard Gibbs free energy of reaction by the standard electrode potential. Then, we can find that the electrode potential is equal to the standard electrode potential, corrected by the activities of the oxidant and reductant. The general form of electrode potential is called Nernst equation. The electrode potential is equal to the standard electrode potential, corrected by the reaction quotient. Pay attention that, in the reaction quotient, the activity of the reductant is in the numerator, the activity of the oxidant is in the denominator. It is independent of the direction of the reaction. At room temperature, RT over F is a constant. The natural logarithm is usually converted to decimal logarithm for convenience. Thus, the Nernst equation is usually used in the following way. For example, silver-silver chloride reference electrode is widely used in scientific research. Let's find the electrode potential of it in 1 molar potassium chloride. In this reference electrode, a silver wire is coated with a layer of silver chloride. The redox pair is silver ion and silver. The electron transfer number is 1. When the silver chloride is in equilibrium with the silver and chloride ion in the electrolyte, the product of the activities of silver ion and chloride ion is the solubility product. Thus, the activity of silver ion can be replaced by the solubility product of silver chloride and the activity of chloride ion. The result is about 0.21 volt. It is close to the value given in the previous table. The electromotive force is the open circuit voltage of a galvanic cell. Since there is no current, both half reactions are in equilibrium. Both electrode potentials can be expressed by Nernst equation. The difference between them is the electromotive force. Pay attention, in a galvanic cell, the electrons move from the anode to the cathode. Thus, the electrode potential of the anode is lower than that of the cathode. And we always subtract the cathode electrode potential by the anode electrode potential. Therefore, electromotive force of galvanic cell is always positive. If you end up with a negative electromotive force, the overall reaction must be non-spontaneous. Electromotive force has such expression. Standard electromotive force is the electromotive force if all the substances involved in the overall reaction are in their standard states. Thus, it is the difference between the cathode and anode standard electrode potentials. The ratio between the cathode and anode reaction quotients is the overall reaction quotient. As a result, electromotive force is equal to the standard electromotive force, corrected by the overall reaction quotient. This is called the Nernst equation for electromotive force. It has the same form as the Nernst equation for electrode potential. On the other hand, each standard electrode potential is related to its standard Gibbs free energy of reaction. The difference in the standard Gibbs free energies of the half reactions is the standard Gibbs free energy of the overall reaction. So, standard electromotive force can be calculated from the overall Gibbs free energy of reaction as well. Let's use hydrogen-oxygen fuel cell as an example. It is a typical galvanic cell. On the anode, hydrogen gas is oxidized to proton. The proton diffuses through the electrolyte to the cathode. Meanwhile, the electrons drift through the load to the cathode. At the cathode, oxygen gas reacts with protons and is reduced by the electrons to form water. Hydrogen-oxygen fuel cells have much higher energy conversion efficiency than steam engines. Moreover, the only waste produced is water. So, hydrogen-oxygen fuel cell is one of the most promising clean energy technologies. However, the electrocatalysts used in hydrogen-oxygen fuel cells are platinum-based alloys, which are very expensive. Thus, commercial hydrogen-oxygen fuel cells are still under development. The cell notation of hydrogen-oxygen fuel cell is shown below. Here, PEM represents polymer exchange membrane, which is the most widely used electrolyte in hydrogen-oxygen fuel cells. The overall reaction is the same as the combustion of hydrogen in oxygen to form water. The standard Gibbs free energy of reaction is twice the standard Gibbs free energy of formation of water. The standard electromotive force at room temperature is 1.23 volt. When air at 1 atm is used, the electromotive force can be calculated using the Nernst equation for it. When a non-spontaneous reaction is desired, an external electromotive force is needed to drive it. Such process is called electrolysis. For example, the decomposition of water is non-spontaneous. The electromotive force of it is the opposite of hydrogen-oxygen fuel cell. To compensate this negative electromotive force, an external electromotive force greater than 1.23 volt is needed. If there is such an electromotive force, the overall electromotive force becomes positive, so that the electrolysis can be started. You can see that the electrolysis of water is just the opposite of hydrogen-oxygen fuel cell. Most metal corrosions are electrochemical processes. For example, iron reacts with oxygen spontaneously. However, in dry air, this process is very slow. When an iron surface is covered by water, it rusts much faster. In water, iron has anodic sites and cathodic sites. At the anodic site, iron is oxidized to ferrous iron. The ferrous ion is further oxidized by oxygen to form hydrous ferric oxide, which is rust. Meanwhile, the electrons drift inside the iron to the cathodic site, where oxygen is reduced to water. Let's consider the electrode potentials and electromotive force of electrochemical corrosion of iron. The standard electrode potential of the cathode is 1.23 volt. Suppose the pH of water is 7, and the activity of oxygen in air is about 0.21. The electrode potential of the cathode is 0.80 volt. The standard electrode potential of the anode is -0.44. For normal water, the activity of ferrous iron must be much lower than 1, so the electrode potential must be lower than -0.44. Thus, the electromotive force must be greater than 1.24 volt. It is a huge electromotive force, so that the corrosion of iron is very favorable. One of the ways to protect a metal from corrosion is cathodic protection. The principle is that, when the electrochemical potential of a metal is sufficiently lowered, the electrons stay with it, so that it is no longer oxidized. One method to lower the electrochemical potential of a metal is connecting it to another metal with a lower electrode potential. For example, the standard electrode potentials of magnesium, aluminium, and zinc are all lower than that of iron. Thus, when one of them is connected to iron, the iron serves as the cathode. Electrons diffuse to iron due to its higher electrochemical potential. This process is like the diffusion of electrons in the p-n junction. As electrons diffuse to iron, its electrochemical potential is lowered, and it no longer corrodes. Another way to lower the electrochemical potential of iron is connecting it to a negative electrode of a direct current power source. Meanwhile, the positive electrode is connected to an inert metal, such as platinum. When enough voltage is applied, the system works as an electrolytic cell. Water is reduced to hydrogen on iron, which is a cathode. Thus, the iron is protected. In such system, the anode doesn't need to be replaced, because it is inert. Here, I show you two examples of cathodic protections and their sacrificial anodes. Rechargeable batteries are electrochemical cells. A rechargeable battery is a galvanic cell when discharging but an electrolysis cell when charging. For example, lead-acid battery has an electromotive force of about 2.1 volt. Its cell notation is shown below. During charging, the anode reaction is the oxidation of lead sulfate to lead dioxide. The cathode reaction is the reduction of lead sulfate to lead. The overall reaction is the disproportionation of lead sulfate. It is non-spontaneous. During discharging, the anode reaction is the oxidation of lead to lead sulfate. It is the reverse reaction of the cathode reaction during charging. The cathode reaction is the reduction of lead dioxide to lead sulfate. It is the reverse reaction of the anode reaction during charging. The overall reaction is the comproportionation of lead and lead dioxide. It is the reverse reaction of the charging and is spontaneous. The schematic diagram showing the charging and discharging of a lead-acid battery is shown below. Pay attention, during charging, the anode has higher potential. During discharging, the cathode has higher potential. Thus, the electrode with lead dioxide is always the positive electrode, regardless of the direction of current or reaction. Similarly, the electrode with lead is always the negative electrode.